Okay, so just a short lesson on molar heat of reaction, also known as delta H. And if you're thinking that that's familiar, yes it is. Remember our enthalpy diagrams. And we calculated the delta H was enthalpy of the products minus enthalpy of the reactions. And that's where we got into the exothermic reactions have a negative delta H, endothermic have a positive delta H. So we're going to basically determine, remember enthalpy is just bond energy. And so heat of reaction deals with where does that energy actually come from? How do they actually calculate how much energy the reactants and products start and end with? So in our first one here, here's how we calculate. It's pretty straightforward. If we have a sample problem, and we have 0.88 grams of propane. We're going to go ahead and calculate the delta H of reaction, molar heat of reaction for propane. It was burned, and what we did here is we have our propane. Here's our burner, and we're collecting all the propane. Now, obviously, we wouldn't use a glass, but we would use a calorimeter. And remember, the deal with calorimetry is heat given off by the reaction is absorbed by the water. So, temperature change of the water, 10,000 grams of water. Temperature goes from 25 to 35.6. So basically, remember calorimetry. We calculate the CP of the water, the mass of the water, change in temperature of the water. Notice we don't even care about the propane. So let's go ahead and do that. So first step, remember our Q formula, okay, is what we're going to use first is Q formula. Find the delta H. Delta H, or heat of reaction, is always in kcals per mole. Mathematical operation that per means is divide. So we need to calculate kcals, or what we've been used to as calories, and then we're going to calculate moles and we're going to divide them. So remember, our units tell us what to do. So Q formula, Q equals CP of the water times the mass of the water times the temperature of the water, 106,000 calories. Well, let's go ahead and turn that into kcals. So kilo is 1,000 times. So 1, 2, 3. We're going to move our decimal, and we have 106 kcals. Now notice I did negative because what we did was we calculated the amount of energy the water absorbed, but it was given off by the propane, and we're calculating it for propane. So that's why I put a negative there, just showing that it's being released or absorbed. Next one is, let's go ahead, so now we have kcals, let's go ahead and calculate moles. So moles of what? Well, moles of propane. We're going to go grams of propane to moles. So we need to look up the molar mass. 3 carbons, they're each 12 grams per mole. 8 hydrogens at 1.0 grams per mole, and we need to add that up. And here's our setup. What goes up must come down. So 0.88 grams divided by the molar mass of propane, 3 carbons, 8 hydrogens, and we're going to get 0.02 moles. Last step, look at our units, kcals per mole. Kcals divided by our 0.02 moles, and we get our final answer of negative 5,300 kcals per mole. So what that means, for each mole of propane that we burned, we gave off 5,300 calories. So let's go ahead and do one more step. Let's go ahead and insert that. And there's lots of steps here. We'll take it through one step at a time. Let's go ahead and insert that into our equation. Here's a complete balanced equation. Propane's burned, and it combines with oxygen. We produce carbon dioxide. Water's already balanced for you. Now, let's go ahead and insert this in the equation. Negative 5,300 kcals are given off per 1 mole of propane. Well, if it's a negative, it indicates it's an exothermic reaction. It's going to go ahead and be on the right side here. Okay, and we're just going to drop that negative because the negative just tells us which side it's on. If it's a positive, it's endothermic, so it's going to be on the left side. You probably remember that. If it's a negative, it's exothermic. It's going to be on the right side. Now, just a little heads up. This is kcals per how many moles of propane? 1 mole is implied. What if there in the equation there were 2 moles in front here? Well, we would just need to go ahead and double that. If there are 3 moles of propane here, we would triple this value, and that's what we'll go there. All right, so you're going to go through and do a few steps of these on your worksheet for this. All right, last one. Now that we know how to put them in an equation, let's go ahead and use it. First of all, the molar heat of reaction is what we've been talking about here. And they use this funny RxN for reaction. You probably remember it like with medicine. And this must be expressed in terms of particular compounds. So here's our sample problem. We have nitrogen monoxide combining with oxygen forms nitrogen dioxide, and it gives off 114 kilojoules of energy. So let's go ahead and do the delta H of reaction. We can actually do it for each of the 3 compounds. So really they have to tell you which compound to do it for. So this one tells you take kilojoules divided by moles of NO. Okay, well, where do we have kilojoules? Well, right here, 114 kilojoules. And we're going to go ahead and divide it by how many moles? 2 moles of NO. Okay, go ahead. Get that pen here. So I'll just do it down here. 114 kilojoules per, okay, that's what that means, per 2 moles. And the reason it's 2 is because we have a 2 as a coefficient of NO. All right, now what we need to decide is this an exothermic reaction? Is this a negative? Why, yes it is, because we have the heat on the right-hand side there. So go ahead and fill out our answer there. 114 divided by 2 is 57. We'll put a negative there because it's exothermic. Another way of saying this is they're on the opposite sides. Right? It gives off heat. All right, next one. Kilojoules per mole of O2. Well, what do we got kilojoules? Again, right here, 114. Notice we're going to use this for each of these. And then how many moles of oxygen do we have? If there's nothing there, it's an implied one. So we're just going to simply divide those. That gives us 114, positive or negative? Negative, good, because they are on opposite sides of the equation. Oops, revealed the answer for you. Okay, almost done. And we'll do a couple more. And we've got last one, kilojoules, 114 kilojoules divided by how many moles of NO? 2. We have 2 moles of NO2. And it's 57, right? Now, this is going to be positive. They're on the same side. Okay? And I'm not going to get too picky with positives and negatives, but let's try and use them appropriate. Okay, so now we can do a couple things with this. Let's say we've got, let's try this. Let's get a sample problem here. Okay, how much energy is released from 4 moles of NO? Well, some of you guys probably do this in your head because you see, oh, there's 2 moles of NO, releases 114 kilojoules. So if 2 moles release 114, 4 moles would release twice that. That's correct. Now, if you can't do it in your head, here's what you want to do. We're going to use this as an equality. And set up a conversion factor. We're going to start with our 4 moles of NO. Now, we need a conversion factor. Well, here's our conversion factor. Okay, right here. Negative 57 kilojoules per 1 mole of NO. Well, we're going to go 1 mole of NO on the bottom. Okay, there's our 1 mole of NO. And then negative 57 kilojoules on top. Moles of NO cancel out. Okay, and we are left with our answer of negative 228 kilojoules. So you can take the delta H, the heat of reaction, and make a conversion factor out of it. That you're going to be doing a couple of those. All right, let's do the next one here. Okay, let's try this one. Let's say we've got, let's do the opposite. Let's say we got 171 kilojoules. And we want to find out how many moles, kilojoules I should tell you, of NO2. And we want to find out how many moles of oxygen we would need in order to release that much energy. Well, we're going to set ourselves up with a conversion factor. We need to find our moles of NO2, and that's the one we're going to use right there. So now what we need to do is decide which of those two goes on the bottom, 57 kilojoules or 1 mole of NO2. Well, to cancel them out, we need to put our 57 kilojoules on the bottom and 1 mole of NO2 on top. So kilojoules cancel out. Should put NO2 there. Okay, kilojoules cancel out, and we're left with moles. So really, it's 171 divided by 57, and that's going to give us 3 moles of O2. Okay, so you could do it one way. I could give you moles, use the delta H to calculate the energy, or I could give you delta H, or I could give you energy, just like I did in the second problem, and you can tell me how many moles there are. All right, good luck.